I'm tackling a machine learning problem using scikit-learn's RBFSampler to reduce the number of features in my dataset from 100 to 50. I need to understand how the gamma parameter affects this process. It's all about the width of those Gaussian functions. The heart of this problem is understanding the gamma parameter within the RBFSampler function in the scikit-learn library. It's how we control the width of the Gaussian radial basis functions used for kernel approximation. To solve this, I'll first recall what gamma represents. Then, I'll think about how different values of gamma affect the localization of the approximation, meaning how focused the kernel's influence is on each data point. I also need to consider its effect on computational cost, even though it's not a direct relationship, and I'll explore what happens with really small or large values of gamma. I'll evaluate each option to see how gamma behaves. I'll determine which statements accurately reflect how gamma impacts kernel approximation and computational aspects. Let's get to the bottom of this gamma mystery. My dataset has 100 features. I'm using RBFSampler to reduce this to 50, essentially simplifying the data while trying to preserve its important structure. Think of it as summarizing a lengthy document by focusing on the key ideas. Gamma helps me control this summarization process. This section presents multiple-choice questions about the gamma parameter. I will choose the true statements based on my understanding of its function in RBFSampler. It's a test of my knowledge, let's ace it. After carefully considering the effects of the gamma parameter, I've determined that options A, C, and D correctly describe its behavior and consequences within the RBFSampler algorithm. I'm confident in these findings. These options accurately reflect gamma's role in controlling localization, Gaussian width, and the approximation's tendency toward linearity. I'm focusing on the gamma parameter within scikit-learn's RBFSampler. This parameter is super important because it directly controls how the radial basis functions behave. Think of it as the tuning knob for our approximation. We start with 100 features in our dataset. Using RBFSampler, I want to reduce the number of features to 50. This dimensionality reduction helps simplify the model and potentially improve performance, while also speeding up computation. It's a common technique in machine learning. I'm using RBFSampler, a scikit-learn tool that approximates a kernel using random Fourier features, to accomplish the dimensionality reduction. Think of it as a smart way to compress our data. I have a dataset that initially has 100 features, but to make things easier to work with, computationally, and to potentially improve the model's accuracy and reduce overfitting, I am reducing this number down to 50. This is where the RBFSampler comes in. I'm explaining the gamma parameter within scikit-learn's RBFSampler. RBFSampler uses random Fourier features to approximate a kernel, and gamma is the key parameter controlling the width of the Gaussian radial basis functions. A larger gamma means a narrower Gaussian, resulting in a more localized approximation. A smaller gamma means a wider Gaussian, resulting in a less localized approximation. Think of it like this. Gamma is like a zoom lens. A larger gamma zooms in, more localized. A smaller gamma zooms out, less localized. This question tests your understanding of the gamma parameter within the RBFSampler and its effect on kernel approximation. We're given a dataset with 100 features and want to reduce that to 50 using RBFSampler. I will now test your knowledge on how gamma influences the approximation. The dataset's initial dimensionality is 100 features, and we are using RBFSampler to reduce the number of features. This is important context for understanding the usefulness and efficiency of the kernel approximation techniques applied. Our goal is to reduce the original 100 features to 50 using RBFSampler. This dimensionality reduction is a common task in machine learning to help decrease computational cost and avoid overfitting. The gamma parameter plays a big role in how effectively this reduction is achieved. I'm using scikit-learn's RBFSampler to approximate a kernel. My dataset initially has 100 features. I want to use RBFSampler for dimensionality reduction. This is the crucial parameter in RBFSampler. It controls the width of the Gaussian radial basis functions used in the kernel approximation. A smaller gamma means wider functions, while a larger gamma means narrower functions. Think of it like this. gamma controls how spread out the influence of each data point is in the approximation. I'm setting the number of components to 50. This means I'll reduce my 100 features down to 50 using RBFSampler. This parameter affects the computation time, but not the GAMMA parameter. It's all about the number of features we decide to keep in the reduced dataset after the transformation. We need to understand how the GAMMA parameter affects the outcome of RBFSampler. It's the heart of the dimensionality reduction technique I'm using. My dataset starts with 100 features. That's my starting point before I begin using RBFSampler for dimensionality reduction. This is the algorithm that I will use to perform a kernel approximation and reduce the dimensionality of my dataset. The GAMMA parameter is crucial for its function. My goal is to get a reduced dataset with only 50 features by using the RBFSampler algorithm. That's my target dimensionality. I'm focusing on the GAMMA parameter within scikit-learn's RBFSampler. It's a crucial setting that we need to understand. Let's dive into the core of this quiz question. We are using RBFSampler to reduce the number of features in a dataset. A larger GAMMA value makes the Gaussian functions narrower. Think of it like this. Each data point's influence shrinks, leading to a more localized approximation. The GAMMA parameter directly controls the width of these Gaussian functions. A smaller GAMMA creates wider functions, spreading out the influence, while a larger GAMMA results in narrower functions. With a very small GAMMA, the Gaussian functions become incredibly wide. The influence of individual data points is so diffuse that the approximation effectively becomes linear. It's like blurring the details until only the overall trend remains. I'll explain what the gamma parameter in scikit-learn's RBFSampler does. It's a crucial part of this kernel approximation method. Understanding it helps you control how precisely the kernel is approximated. We start with a dataset having 100 features, meaning each data point is described by 100 different characteristics. This is our starting point. We want to reduce the complexity without losing too much information. The gamma parameter in the RBFSampler controls the width of the Gaussian radial basis functions. Think of these as bell curves that shape our approximation. A higher gamma value means a narrower bell curve, a more localized influence. A lower gamma value creates a wider bell curve with a broader effect. RBFSampler is an algorithm from scikit-learn that helps reduce the dimensions of your dataset. It does this by using random Fourier features to approximate the kernel. It's like taking a shortcut to calculate similarities between data points more efficiently. I like to think of it as a dimensionality reduction tool for your machine learning model. The value of n_components, number of components, indicates the reduced dimension, here, 50. We aim to reduce the 100 features down to just 50 using RBFSampler. This reduces the computation load while trying to preserve the important information in the data. This is one of the key goals of dimensionality reduction. This question tests your knowledge of how the gamma parameter within the RBFSampler affects the transformation of your data. A larger gamma results in narrower Gaussian curves, which leads to a more focused or localized approximation in the RBFSampler. This is false. While an extremely small gamma could indirectly lead to needing more components for accuracy, thus increasing computation, it does not directly affect computation cost. The main computational cost is related to the number of components, not the gamma itself. Gamma directly controls how wide or narrow the bell curves, Gaussian functions, are. It's the primary way we control the localization of the kernel approximation. A very small gamma makes the Gaussian curves extremely wide, effectively making the approximation more linear. The influence of individual data points becomes less significant, and it's like we're approximating a simple linear relationship. This quiz focuses on understanding the _gamma parameter within scikit-learn's RBFSampler, a tool I use for dimensionality reduction in machine learning. I'll test your knowledge of how _gamma affects the algorithm's behavior. Get ready. I'm using RBFSampler, radial basis function sampler, from the popular scikit-learn library to approximate a kernel, which is a way to measure similarity between data points. My goal is to reduce the number of features in my dataset from 100 to just 50. This is my initial dataset, with 100 individual characteristics for each data point. I need to make it smaller for efficiency and potentially better model performance. After using RBFSampler, my goal is to reduce that to 50 features, maintaining the essential information from the 100 features. This is the specific function I am using from the scikit-learn library to achieve the dimensionality reduction. It uses random Fourier features to approximate a kernel, speeding up computation. I'm taking a 100-dimensional dataset and applying the RBFSampler with a gamma parameter. This transforms the data to have only 50 dimensions while trying to preserve essential information for downstream tasks. This is the key parameter I'm focusing on. Gamma controls the width of the Gaussian radial basis functions used in the approximation. It directly impacts how localized or spread out my approximation of the kernel will be. If I increase gamma the Gaussian functions become narrower, leading to a more localized kernel approximation. I focus more on local similarities. While it might seem that decreasing gamma making the Gaussian wider, would increase computational cost, it's not a direct relationship. The computation is mainly determined by the number of components I choose in my RBFSampler, not directly by gamma. This statement correctly describes the role of gamma. Gamma directly determines the width, or spread, of the Gaussian functions involved in the kernel approximation. With a very small gamma I have very wide Gaussian functions, which means I essentially average over a large area and approximate my data using a simpler, almost linear, transformation.